Okay, now, assuming you understand compound interest, it's a pretty easy transition to population models. We have a population. We have 500 critters, and their population increases by 5% every year. Well, if something increases by 5% every year, and T is your number of years, you're going to multiply your initial population by 1.05 to the T to find the population after T years. Review the reasoning that we used to develop the idea of compound interest. Interest just being compounded annually. Okay? So for population models, usually we have what's called a growth rate, which would be 5%. It's an annual growth rate. And we know that if we increase something by 5% every year, T is the number of years, that's the same as multiplying it by 1.05 for every year, because increasing something by 5% is the same as multiplying it by 1.05. A concept you should lock in very tightly, review it if necessary. Okay, 1.05, anyhow. So we multiply whatever the initial population was by 1.05 to the T. So if T is the number of years, starting at the time we have 500 critters, 500 times 1.05 to the T is how many we're going to have after T years. Okay, so we could find the doubling time, but of course we did that in preceding video, so there it is. Okay, we could relabel the graph of the basic exponential function to represent this population. And here we would have then our population curve, and we can see how the population takes off with time. After 36 years, of course you might not feel like waiting around that long, although I'll tell you 36 years can go pretty quick. After 36 years we're going to be here, then after 72 years we're going to be here. Now 72 years, that doesn't go all that quick unless you live to 90 or so. But there we have it, okay? So now our estimate of P of 50 is going to give us what? Well, P of 50 is 1,270. That's the population after 50 years. So I can now say, okay, let's let T be in years, and let Y equal population. So now we have an interpretation for this graph. And then we have an interpretation for the slopes of this graph. And the slopes of this graph become important. Let's say one of the reasons the population of these critters is only growing by 5% a year is that we kill 5% of the population every year, and they're reproducing at a rate that still allows them to grow at 5%, or maybe we kill off 10%, still allowing them to grow by 5%. This tells us how much more food we're going to get, assuming we're using these critters for food. And whatever your take on using critters for food happens to be. Okay, so some people don't like the idea. But it happens, so here we have it. And if the critters happen to be fish, people are usually less squeamish about it. So let's just say it's a population of fish in thousands or millions or whatever. So we fish out 10% of the population every year, but they still reproduce at a rate that allows them to grow by 5% annually. So this means we're going to have more food, and the rate of food production is going to keep increasing every year. We could compare that to the rate at which our population is increasing to see if everybody's still getting the same amount of fish. Okay? So the rate at which this population grows can be a very relevant quantity. And we might want to do an estimate of the rate at which the population grows. So, at what rate is it growing, let's say, between this point that we estimated and this point? Okay, well, that's going to be the slope of our fundamental triangle. Okay, in our delta x, let's just draw the triangle again and label the coordinates of the points. This point is at 50, 12, 70, according to our estimate. And this point is at 65, 1700, according to our estimate. So we want to analyze the slope of the triangle. Okay, well, the run goes from 50 to 65. So it's going to be 65 minus 50, and that's in years. 15 years. The rise from 1270 to 1700 is 430. That's in critters. Okay? So the slope, well, I'll write the calculation out here and then I'll label it. $430 critters over 15 years, which is what? It's 28 1/3 critters per year. If I did that arithmetic correctly. Wait a minute. It's 430. Yeah, that's right. No, it's 2/3. Okay? So the slope is (28 2/3) critters per year. And that's what applies to this triangle here. So you would, if the triangle's a little bigger, you could label it here. But we could put the slope down here, 28 2/3 with this around it tells us that that slope is this. And what's that mean? Well, it means that every year you're going to get 28 2/3 more critters. Okay? And that's, the population is going to be that. Now, if you're taking 10% of the population, it gives you 2.8 2/3 critters. If they're very big critters, like your Eskimos hunting whales, that could be significant difference between survival and non-survival if your population keeps increasing. If it's in millions of smaller critters, you interpret it accordingly. Okay, so there's an example of a population model, an exponential population model, and some interpretation, construction of, and interpretation of at least one aspect of its graph.